Hello everyone, I am Mark Joseph Panong, a third-year mechanical engineering student from Section 3A. We are back again with another tutorial video, but today, we are going to solve problem with regards to moment area theorem. But first, let us recall what it is all about. The moment area method is one of the most effective methods for obtaining the bending displacement in beams and frames. In this method, the area of the bending moment diagrams is utilized for computing the slope and or deflection at particular points along the axis of the beam or the frame. The moment area method is composed with two theorems. Theorem 1 states that the angle between the tangents at any 2 points on the elastic curve equal the area under m over ei diagram between these 2 points. On the other hand, Theorem 2 states that the vertical distance between the tangent at a point A on the elastic curve and the tangent extended from another point B equals the moment of the area under the m over ei diagram between these 2 points A and B. From the book Mechanics of Materials 4th edition, we are asked with a problem 9.9 which states that for the uniform cantilever beam and loading shown, determine the slope and deflection at point B and point C. To solve this, the theorems will be utilized on solving moment area problem. Step 1 is to show the analyzed free body diagram based on the given loading condition in figure 9.99. Then, for step 2 is to apply the condition for force equilibrium along the x direction. As you can see, for the summation of forces along x-axis is equal to 0. Therefore, Ax is equal to 0. Next is to apply the condition for the force equilibrium along the y-axis. We have the summation of forces along y-axis equal to 0. Therefore, we have Ay equal to WL over 2. Step 3 is to use the moment equilibrium condition to calculate the moment about point A from the free body diagram. Then we have the moment about point A equal to negative 3WL squared over 8. On the other hand, the moment about point C is equal to negative WL squared over 8. Step 4 is to illustrate the bending moment diagram by parts and indicate the equation in each areas. Now for step 5, at point of support A, the change of slope in deflection is 0. So in finding the slope at B, we have the first equation written in green, that one. Now for the tangent to the elastic at the fixed end A is known as cantilever beam. Now that is equal to 0 and we are going to use it as a reference tangent. So we are going to substitute 0 as slope at A in equation 1. Now we have theta B is equal to theta B over A. For step 6, we are going to use the first moment area theorem equation given. That is theta B equal to A1 plus A2 plus A3. To find the slope at B is we are going to add all the areas given from the analyzed bending moment diagram. Therefore, we have the slope at B equal to negative 7WL cubed over 48EI. With the same manner, we can find the slope at C using the equation 2 written in green, that one. The tangent to the elastic at the fixed end A is known as cantilever beam, that is theta A equal to 0, and we're going to use it as a reference tangent. Then, we have to substitute 0 as slope at A in equation. Therefore, we have theta C is equal to theta C over A. For step 8, we are going to use the moment area theorem equation to solve for the slope at C, that is equal to A2 plus A3. Then, substitute the values of specific areas given. Therefore, we can have the slope at C that is equal to negative WL cubed over 8EI. Now, this one here shows the centroidal distance inside the beam given. This diagram will be utilized in solving the deflection at point C and point B. To calculate the deflection at C using the relation, first is to set the reference tangent at C in horizontal, and then the deflection at C is equal to the deviation of A with respect to the tangent at C. That gives us T A over C equal to YC. And then we can also use the second moment theorem given, that one, that color green. Here, the centroidal distance of the rectangular portion AB is the centroid at x2 bar, and the centroidal distance for the triangular portion AB is the x3 bar. By substituting all the given values, we can now conclude that the deflection at C is equal to negative 7WL to the power of 4 over 192 EI. With the same manner, we can calculate the deflection using the same relation, but our YB here is equal to YC plus A1 x1 bar. Then, substitute the YB as deviation of A with respect to the tangent at B. Now, that gives us equal to YC plus A1 x1 bar. In this case, the centroidal distance of the triangular portion is x1 bar. Therefore, calculating all the given values, we can now have the deflection at B equal to negative 19 WL to the power of 4 over 384 EI. Therefore, the slope and deflection at points C and B are shown. That's all. Once again, this is Mark Joseph Panong from MA3A. Thank you for watching. Peace out!